I'm Jeremy Hilton. I'm the Vice President of Processor Development at D-Wave Systems. I'm responsible for the Processor Development Group, which involves the design, test, and development and release of the quantum processor that D-Wave makes, which is the underpinning of the quantum computers that we build. Each of these black systems is a quantum computer. Inside that system is a thumbnail-sized quantum processor. In order to operate and develop quantum processors, we require a fairly extreme operating environment, which includes ultra-low temperatures and an ultra-low magnetic environment. And to achieve those, we need a fairly large and sophisticated system. The main room behind us houses the quantum processor, and the data racks in the front hold the quantum server, where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in. If you look inside the data racks, you'll see that they don't contain what you would normally expect. So here we have some scroll pumps, which are mechanical parts associated with pulling vacuum on the fridge inside the room behind. So this is obviously highly unusual for a data rack, but has been integrated so that it wouldn't look out of place in a data center. And in fact, the requirements for running the system are consistent with all the services that would be available in a data center, which would include chilled water and power predominantly. In this rack is the quantum server, which allows users from anywhere in the world to interact with the processor itself. This server is receiving information from users, converting that into the machine language of the processor, and sending that machine language into the room behind, where high-precision analog electronics will convert those signals into electrical pulses, which are sent through cables into the refrigerator and down through the cooling system to the ultra-low temperature of the processor. It executes its problem, and then data from the processor is returned to the server and returned to the user. And the system is very flexible, and that users can be programming in whatever language they're comfortable with, and interacting with it either with this system in their data center or even here in D-Wave's lab. The quantum bits in our processor store information in the form of little magnetic fields. The 0 and 1 correspond to a little magnetic spin. The controls over the qubits are all in the form of magnetic fields. So the quantum processor is very sensitive to magnetic noise and the magnetic environment that it sits in. In order to keep that magnetic environment really low, as well as support the ultra-low temperature that it's operating at, this system behind me has about 16 layers of shielding between where I'm standing and where the chip sits at the center. These black panels are really for aesthetic purposes, and they integrate these data racks with a shielded room, which is the first of those layers of shielding, and is filtering out RF signals. So if you were to stand inside the room and close the door, your cell phone would stop receiving a signal. The fridge itself has a combination of radiation shields as well as magnetic shields, which help support the ultra-low temperature operating environment and achieve the ultra-low magnetic field. Inside the room, we have to keep electromagnetic noise very low. So even things like power outlets aren't allowed, because power can be quite noisy without extensive filtering. So inside the room, we have the cooling system, and these are radiation shields. So this is the next layer of shielding inside the room. The chip itself, the quantum processor, is sitting at the bottom of this array of shields. And this is, again, the first of several more layers. Inside these shields is vacuum, which is the insulation of the cooling system. When we want to swap the processor or conduct maintenance on the fridge, we warm the system up, we remove these shields, and then the processor is accessible, as well as all of the internals of the refrigerator.
My name is Murray Tom. I'm the Director of Professional Services at D-Wave. I talk with our customers and partners about what quantum computers are, what kind of problems that they solve, and work with them to develop software that uses quantum computers. We're standing inside a quantum computer, and you may know that the quantum world is delicate. It's easily disturbed. So there are many layers of shielding in this system, which we've removed in order to look at the internals here. A traditional supercomputer may have many thousands of processors in it, but in this quantum computer, there's only one chip located right down here. When you send an instruction to the quantum computer, a delicate quantum calculation is taking place on that chip to produce your solutions. The system we're looking at here is an ultra-low temperature cryogenic fridge. Because it works at such low temperature, we use the Kelvin scale to measure how cold it's getting. In the Kelvin scale, a warm room is like 300 Kelvin, and 0 Kelvin is the lowest temperature that can be reached. Physicists refer to it as absolute zero. There's two levels of cooling in this system. The top one is a pulse tube refrigerator, which takes us from 300 Kelvin to 50 Kelvin, and then down to 3 Kelvin. This is roughly the temperature of interstellar space. And then a second refrigerator, a dilution refrigerator, takes us in this plate from 0.7 Kelvin, 0.1 Kelvin, and then down to 0.01 Kelvin. When the system is operating, this plate and everything mounted below it is 10,000ths of a degree above absolute zero, which is more than 100 times colder than interstellar space mounted here. And this whole system is designed to sustain those low temperatures in a continuous cycle. When you send an instruction to a quantum computer, the signals pass down these wires along the sides of the refrigerator, and at this point there's a break in the wires where all the signals become superconducting. Superconductivity is this amazing effect where you can send electrical signals without any resistance whatsoever. So the electrons aren't even interacting with the atoms in the wires around them. That's great because it means that this portion of the system has no energy dissipation, it produces no heat. But it also means that we can't rely on the wires to cool the electrical signals and eliminate their noise. So we have a custom filter bank mounted here which cools those electrons. An important aspect of the superconductivity is that these signals and the quantum processor unit consume virtually no power, whereas the supporting systems around it consume about 15.5 kilowatts. And this remains the same regardless of which processors are installed at the bottom. If you were to take a fully populated server rack out of a traditional supercomputer, it might consume 10 times that much power. So for our first customer, Lockheed Martin, when they upgraded from their first chip to the D-Wave 2, they saw a relative performance improvement on the order of 10,000 times, but the power consumption for the system was the same.
Hi, I'm Mark Johnson. I'm a scientist at D-Wave Systems, and I work with a team of other scientists and engineers developing the superconducting integrated circuit chip that's at the core of our quantum annealing processor. We have our chips fabricated on 8-inch silicon wafers, and when we receive them back from the foundry, they look like this. Here, if you look closely, you'll be able to see a repeated array of squares that are multiple copies of our integrated circuit chips. That integrated circuit chip is really just a series of metal layers, predominantly, which you can see in cutaway here. The process that goes into fabricating this integrated circuit chip is actually not that different from that which goes into making the chip that drives your cell phone or your laptop. One of the principal differences, though, is that these metal layers are actually made up predominantly of niobium, and niobium is chosen because it's a superconductor. So the thing about a superconductor is that when you cool it down below a certain temperature, all of the electrons really collapse into the same quantum state. They cooperate with each other in the way that electrons in a normal metal don't. Now, ordinarily, quantum mechanics only exhibits on the scale of atoms, electrons, or photons. Superconductors are unique in this way in that you can see quantum behavior on a much larger scale. And it's these properties, these quantum mechanical properties, that enable us to use these materials to make our quantum processor. So this is a blueprint of one of our processors. The design and construction of one of these is not really that different from that of a conventional processor, but a really important difference is that on a conventional processor, the ones and zeros are encoded as voltages and currents on that chip. In this processor, that information is actually encoded in small magnetic fields called single flux quanta, or quanta of magnetic flux. When we're programming the processor, we load hundreds of thousands of these flux quanta into the chip, into various circuits. Then the processor undergoes this algorithm, quantum annealing, which is how it solves the problem that we've posed to it. At the end of that, the answer is in the form also of magnetic flux quanta, which are then pulled out of the processor to the four corners and then up into the room temperature electronics and onto our conventional computer. So the basic computational element in a quantum processor is a qubit. Now, a qubit is a lot like a bit in the sense that it can encode a state as 0 or 1, but it's a quantum bit, Q for quantum bit, and it has the additional property that it can be in a superposition of 0 and 1 at the same time. So this chip is made up of repeating tiles or unit cells, and each one of them is made up of 8 qubits. Now, if you take one of these unit cells, well, we can blow it up and get a better view of it here. So our qubits are actually superconducting wire loops that are interrupted with a circuit element called a Josephson junction. And we make our qubits long and thin. You can see that there are 4 of them running vertically here, and another 4 running horizontally here. Wherever these qubits cross or intersect with each other, we put a tunable coupling element that can be used to allow the qubits to influence each other in a programmable way. A qubit is engineered so that there are 2 stable states corresponding to circulating current going clockwise or counterclockwise. And associated with those 2 stable states are magnetic field either coming out of the surface or into the surface. And they correspond to the 0 and the 1 state respectively for the qubit. Of course, a qubit can be in a superposition of 0 and 1. And so in this case, that means that these qubits can be in a superposition of those 2 circulating current states going clockwise and counterclockwise at the same time. So the idea that a macroscopic object like a wire loop could really be in a superposition state of circulating current going clockwise and counterclockwise is counterintuitive. It's quite odd. But this is the sort of thing that happens in quantum physics on the microscopic scale. And this is exactly the sort of phenomenon that we're harnessing to make our quantum annealing processor.